Mondays, Wednesdays, Fridays, the 11 to 12 slot in this room. And you have a weekly tutorial on Thursdays. So your room number for the tutorial will be conveyed over email. There are 10 sections, and tutorials will be in the tutorial block. So my name is K. Muralidhar. I am from mechanical engineering. So this textbook this course has two parts: fluid mechanics, and the second part is rate processes. They look distinct, but they are in a way connected. So that connection we will see as we go along. So fluid mechanics is roughly 80% of the course, and rate processes would be 20%. So rate processes will include topics like heat transfer, mass transfer. Heat transfer is when you heat up an object and it cools down. Question is, how rapidly is it cooling down? If you blow against the object, it will cool faster. How do you make predictions of this cooling process? Mass transfer, let's say you have a layer of salt in a beaker containing water, and salt slowly diffuses into that water. How rapidly will it go into solution in water? This is a mass transfer, it's mass of salt diffusing in water, that is mass transfer. Or a drop of water evaporating, it is an example of mass transfer. While fluid mechanics deals with, by and large, fluid flow. Okay. You have an AC system in this room, which is blowing air, it's circulating. So air is in motion in this room as we talk. You might have seen waves on oceans. You might have seen little fans running in your inside a computer. It's blowing air, so it remains cool, the electronics. You might have seen water being pumped through tubes in your hostels. The question is, how big should the pump be? If you can estimate, then you buy the right pump. If you buy too small a pump, you won't be able to send it to the third floor or the sixth 6th or 7th. If it's too big, you are paying excessively for it. So, it's good to estimate what are the principles that go behind this estimation. This we would like to study in this course. That is the fluid mechanics part. The textbook for the fluid mechanics part, for heat and mass transfer, I will tell you by and by. But let us start with fluid mechanics. The textbook is called, well, Fluid Mechanics. By Frank White. So, this is a very popular international book. Right now, it is into its 8th edition. I think Indian editions are available. You can buy at a reasonable cost from the bookshop. But our library has a few copies of the 7th edition kept in the reserve section. So, I intend to assign problems from the 7th edition, but I will give you the full problem statement. I will not just give you problem number, I will give you the problem statement, both for tutorials as well as for practice. Now, an advantage of using this book is, whatever edition you use, it has problems and it also has the final answer. Because it has gone into multiple editions, I think most of the solutions are correct. So, I write here, seventh or the 8th edition. We will start with this book. So, let us announce the grading policy. There is nothing unique about it. Four quizzes, 2 before the midsem, 2 after the mid semester, probably 1 makeup at the end, amounting to 10%. These are essentially practice problems, so you remain invested with the course. Tutorial, this 10% will include attendance and any other assignments the tutor may give you. So, this will come to me from the tutor, but certainly attendance will be a part of it. Mid semester will be 30% and final 50%. The final is a 3-hour exam, mid semester is a 2-hour exam. Quizzes will be 20 minutes each, to be held during the tutorial. So, please write this down, and then okay, for the HMT part, heat and mass transfer part, I will give you the book, textbook later. The course contents also I will circulate over email. So, you have an idea of what it is all about. Now, if you go to the library, you will see literally hundreds of books on fluid mechanics. Two reasons for it. One is it has evolved and it has been developed over, let us say, at least 2 centuries, if not more. The second is it's very important. Apart from being widely found, if you think of air, water, oils, they are abundant. A very large number of engineering devices employ fluids, whether you have engines, turbines, fans, compressors. If you think of devices, they employ fluids. So, it is in our interest to know how they behave under a variety of conditions. Okay, so, you might have read in the newspapers, there is a nuclear power plant along the coast of the country, and international organizations pose this question: if there is a tsunami, will your buildings survive or will they collapse? To answer this question, you should be able to predict the force acting on the building arising from the tsunami waves. If a wave hits a structure, what will be the force acting on it? Will the force be so large that it is going to crumble? So, even your hostel buildings, some time ago, the limit used to be 3 floors, then the limit was raised to 4. Now, I think it is 6 or 7, but anything more, if you are on the 8th floor or 10th floor, or of course, buildings can be much taller. If you live there, you will see that the air breeze is the most dominant external factor. So, these are called aerodynamic forces. If they arise from water, they are called hydrodynamic. These forces are enormous. So, beyond a certain point, the building design is essentially controlled by fluid forces. How much are these forces? So, you have to understand the subject of fluid motion to predict quantities like forces. It is these forces which we exploit in devices and extract work out of them. So, it becomes a fluid mechanics problem that way. Of course, apart from air and water and oils I mentioned, you might have done, some of you might have done, or maybe you are doing it now, a course on what TA201, some manufacturing type course, where you carry out machining operations and you pour a huge amount of liquid at the tool tip to keep it cool, to keep its temperature within limits. So, how effective is that cooling liquid from the manufacturing perspective? So, you would be needing tools and techniques based on both fluid mechanics. It involves heat transfer, you are cooling it. So, fluid mechanics and rate processes becomes the foundation to address that question. You might be interested in knowing that as the tool moves against the workpiece, you have these chips generated. Now, the chips flow out of the workpiece. Workpiece is solid, tool is solid, but if you look deep into it, I am talking about figuratively speaking, do not look deep into the cutting process, it is extremely risky. Yeah? So, if you just imagine the chip formation, the chip moves like a liquid. It is called a plastically deforming material, behaves like a liquid. So, there are very amazing applications of fluid mechanics in very distinct and different contexts. If you think of the human body, you have blood which is circulating nutrients. If you take medicine, it is distributed by blood. It is blood which cools our brain and keeps our body metabolism in, let us say, fighting fit condition. So, how does blood move? Of course, there is a pump inside, which is human heart, which keeps the circulation intact. But blood is everything, it goes everywhere. Its movement is determined by the principles we will study in this course. So, applications are many. As a result, books are also very many. You can read any book you want, but I will stick to fluid with this Frank White, because first of all it is a popular book, and second it will help us maintain consistency in giving questions, both for the tutorials as well as for the exams. Okay. We will also borrow some tables and graphs from this book. So, make sure that a copy of this book is available either with you or with your friend. So, quickly you should be able to access this book. So, I am just looking for it's a new page. Huh? So, which tells you that if there is something important, please write it down. I see your notebooks completely closed. It's good to write as we chat. So, I think you are doing a course on thermodynamics. Some of you might have done it. In any case, thermodynamics is covered to some extent in your high school. So, in a way, fluid mechanics builds on ideas covered in thermodynamics. is an idea of a pure substance that is often mentioned in the initial part of thermodynamics, where the material is taken to be chemically homogeneous. So, air, water, oil, whatever we talked about, blood, etc., these are all in a way they are pure, because you take a sample of air here or over there. Maybe if you take a sample of air over there, the CO2 content may be slightly higher, O2 will be slightly lower, but it is also air conditioned. I think by and large the chemical composition will be uniform. Same thing with sea water all over the planet. By and large, sea water has salts. That relative proportion also turns out to be nearly the same. This water, I think the water you drink in the hostels is groundwater. You drink that water, I drink it in my house. The chemical composition is about the same. So, we may approximate air and water, that will be the focus of interest, or oils for that matter, to be pure substances. That is one. The second point that needs to be introduced has to do with the scale at which the study is being carried out. Okay. So, in your courses on physics, for example, suddenly you go into the atomic scale. The scale becomes smaller, 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 smaller. You are looking at elementary particles. But when you talk about a pump or a fan or a turbine, the devices are all at, you may call them human scale, sometimes called the macro scale. So, even if you take a small portion of the fluid medium, let us say I pick 1 mm cube, it is a real tiny portion of the fluid medium. It will have, I do not know, 10 raised to 16, or it's a very, very large number of elementary particles. And so, their interactions, they tend to, you may say, average out, but they manifest in a very different way on the macro scale. So, you can't see those elementary interactions, but you feel them in a very different manner. So, in this course, we will be on the macro scale. The term used for the macro scale is continuum. So, we are on the continuum scale. So, this fluid mechanics is also referred sometimes as continuum mechanics. So, if you have a jet of water, take a tube and you have water gushing out, the particulate nature of matter hardly manifests. You can't really identify one particle versus elementary particle versus another, but you can think of fluid particles. Each fluid particle has a very large number of elementary particles. So, the observable quantity that is available to you the simplest form would be material density. Okay. So, you have to distinguish between density of the elementary particles versus density of the material as a whole. So, suppose you want to find density of glass, you may just weigh it and divide by volume, mass per unit volume. This is a definition adopted on the macro scale. So, for air or water, essentially it is mass per unit volume. So, since we are talking about scale, you may wish to examine how density varies. Density, the symbol often used is rho. This is a Greek symbol. So, since we are planning on working with elemental volumes, let me use this symbol delta V for elemental volume. So, you do a weighing experiment, you work with a volume which is 1 meter cube, air from this room 1 meter cube, you weigh it, mass upon volume will give you the density, it will be the average density of air contained in that volume. And then let us say you bring it down to 1 liter, which is 1,000th of 1 meter cube, 1 liter of air. So, this is a thought experiment. So, progressively you are making it smaller and smaller. Just anticipating the result. Okay. So, in this room, you are carrying out this experiment in a room, in this room. So, probably this delta V is changing over several orders of magnitude. Okay. So, it is a log scale. All right. So, units will be, you may put meter cube or microns, you are going from meter cube to microns to much smaller than that. What will happen when it becomes really tiny? What will happen is the particulate nature of matter will show up. So, in that small volume, you have particles that are moving all over the place, and some particles are out. So, when you carry out that measurement, some particles are out. You carry out the measurement again, the particles are in. So, you start seeing fluctuations in density. These fluctuations will become larger and larger as the volume selected becomes very small. So, this graph on the left hand side will start showing oscillations like this, and density no longer is a relevant property of the material being studied. So, at very small scales you can't use density, you can use density only on larger scales, where these elementary particles are very large in number. So, suppose you have 10 raised to 16 particles, a few of them go in and out, it is not going to matter, okay, and your density will be a stable value. So, since we know the properties of elementary particles, you can actually estimate the volume at which fluctuations are going to be set up. Okay. So, roughly this limit is well, it's called the continuum limit. So, somewhere here would be 1 mm cube. 1 mm cube is huge compared to the continuum limit. That limit of course is material specific. turns out to be very small. So, from the engineering viewpoint, even a small element of the fluid is well beyond the continuum limit. So, even a small portion of the fluid volume can be treated as a continuum, okay, which also tells us that we need not bring in the behavior of elementary or elementary particles. Okay. So, if you are in the continuum scale, then what are the laws of physics that hold at this scale? If you are at the scale of elementary particles, you will have to factor in the structure of the atom. Broadly speaking, the applicable physical law would be the Schrodinger's equation. Okay. But when you reach the continuum limit and beyond, Schrodinger's equation still holds, but it holds now for a collection of a very large number of elementary particles, and a new kind of a law is what is manifested, which is what we see at our scale. Okay. So, at our scale we are able to define density. Okay. So, what are these laws of physics that are perceptible at the macro scale or the human scale or the continuum scale? So, these are the conservation of mass, so very quickly you will recall that such a principle cannot hold at the atomic level, but at the continuum level mass is conserved. Newton's laws of motion, the laws of thermodynamics, so why do we need these principles? These principles will tell us how flow would be set up. If you turn the pump on, how much of flow will take place? If I direct the jet of water on the wall, what is the force that will be experienced by the wall? All the way to a tsunami hitting hitting a nuclear power plant. So, it stretches all the way from roughly, let us say, 1 micron cube. Okay. So, the range, if you want to think of the range of scales, you are going from 1 micron cube to probably a few hundreds of kilometer cube. Okay. So, the Earth's atmosphere, the oceans, waves created, all the way to flow in a tube of your water network in the hostel. So, this network also has multiple scales, going from your wing to the hostel complex, to the academic area, to the city of Kanpur, to the state of Uttar Pradesh, and so on. So, over all these scales, these are the applicable laws of physics, and you can, and how exactly it is to be done, that is what we will study. We will be able to answer very important questions that are of absolute and immediate relevance to all of us. So, these are to be contrasted with well, you have to contrast continuum mechanics with quantum mechanics. In quantum mechanics, you are at the particulate level. Probably you can factor in the interaction among a few particles, but now you have a very large number of particles, and a new kind of reality has set in, where the principles or the natural laws are those of continuum mechanics. So, these principles are then utilized to answer important questions that we face as human beings or in the society. Now, this is all very general, but in this subject, in this course, we are going to limit our attention to fluids. Now, fluids come in various shapes and sizes. So, shapes, I should say, various types. But we will be looking at those fluids which classify as a pure substance. Examples of which oh, it's your mobile ringing. I think we have an institute policy on mobiles. Essentially, we are not allowed to use our mobiles either during the class or during exams. Please keep them off. So, when we talk about fluids, we will be thinking of materials like air, water, oils. Okay. Now, blood has some complexity, because if you look at blood in great detail, it contains particulates. So, it is like a solid liquid mixture. So, behavior is somewhat complicated, but the treatment using the laws of physics continues to hold. See, these laws of physics are material independent. Okay. So, that we will comment upon later. So, right now the scope of the discussion includes air, water and oils. So, these media we have seen are characterized by a density rho. Okay. So, this density can be measured as mass divided by volume at whatever scale. It could be at a small scale or a large scale, but within the continuum range, it is characterized by a density Now, these elementary particles have their own interactions at the small scale. So, they manifest as internal forces on the large scale. So, if you read up books on thermodynamics, those books will tell you that a pure substance will be characterized by an internal pressure and temperature. If you have a chemically inhomogeneous medium, then the chemical composition changes from point to point. If it is homogeneous and chemically homogeneous, then this pure substance will have an internal pressure and it will have temperature. Of course, these are not just constants, they may change from point to point, but they you can measure or perceive, you can feel on the macro scale an internal pressure and temperature T. Symbol we use for pressure is P. This is P, pressure and temperature, and this density will depend on pressure and temperature prevailing at that location. These arise, for example, you might have studied kinetic theory of gases, where at the small scale, so this room, even if the AC is turned off, it may look like a stationary body of air. You take water in a beaker and keep it on a table, looks stationary, but kinetic theory of gases will tell you that at the small scale, particles are in a state of movement. So, that is not factored in on the continuum scale, but because of that movement, the particles, let us say, will hit the walls of the container and will generate a quantity called pressure. So, pressure arises, pressure is a net effect of interactions among elementary particles. So, a small scale feature gets factored in our large scale analysis through properties like pressure and temperature. So, pressure P and temperature. Now, in the first part of the course, mainly while dealing with fluid mechanics, we will think of the material to be at the same temperature. So, that is called isothermal, the medium is isothermal. So, everywhere it is the same temperature. While studying heat transfer, will allow for temperature to change from one location to another. So, so if temperature is constant, then rho is only a function of pressure. But even otherwise, let us say for gases, you might be familiar with the ideal gas law, okay, which relates density to pressure and temperature. So, the origin of the ideal gas law is, of course, interactions among elementary particles to a first approximation given by kinetic theory of gases. Okay. So, if you integrate kinetic theory of gases, you will end up with the ideal gas law. So, what is that ideal gas law? It is rho, what is it? P over rho equal to R T. Okay. So, and you also know that it is applicable over a range of pressures and temperatures. So, for gases, we have a model equation that relates density to pressure and temperature. If temperature is constant, then it is only a function of pressure. So, that is clear. Suppose you take a closed vessel and you try to pump gas into it, pressure inside will keep increasing, and so also will density. On the other hand, for liquids, the change in density with change in pressure is very small. So, let us write down for gases, you have this relationship, while for liquids, by liquids I have water in mind, or could be oils. Rho is practically a constant. Though it may change with temperature, but we are not going to think of temperature changes in the beginning. So, for us density constant, meaning it does not depend on pressure. So, such a material is said to be incompressible. So, these are relations that define density on the macro scale or in the continuum scale. So, these expressions are to be contrasted with the laws of physics I wrote down: conservation of mass, Newton's second law of motion, laws of thermodynamics. So, these are quite distinct from the expressions written here. These are expressions that relate density to pressure and temperature. Why pressure and temperature? Because we are dealing with a pure substance. So, if P and T are specified, the material density is also prescribed, it is fixed. Okay, so, so such expressions are called equations of state. They relate to the internal structure of the material, which on averaging across a hierarchy of scales will display behavior at the continuum or the human level. So, when you carry out an experiment, you can always take a container of water and heat it up and measure the change in density. Okay. You will see some variation in density with temperature, but suppose you pressurize water, you may see no change in density. You pressurize air and you will see density going up with pressure. So, these are at the human scale, but these arise from elementary interactions at the particulate level. Okay. So, manifestations of small scale interactions on the continuum scale. These are to be contrasted with the laws of physics at the continuum scale. Let us say conservation of mass. So, this is not a result of interactions at the elementary level. These are observations on the large scale itself. Okay. The same is true for Newton's laws of motion as well as the laws of thermodynamics. Okay. So, let us stop here and let us just quickly review what is it that I said today. I have given you the name of the textbook, grading policy I have given you, attendance policy I have given you. Attendance will be counted in the tutorials. And then we talked about the continuum approximation. Okay. We talked about pressure and temperature as internal variables in the medium arising from the internal structure of the body, of matter. So, next time we will continue with our discussion on pressure. Okay. This plays an important role in the subject. I just want to make sure, see, those who come late may want to come and sit in the front. If you occupy the last row, are you able to see this? Yes or no? Yes. Are you able to hear me? Okay. Where are the speakers in this? Oh, those are the. I can't see the speakers. Where are the speakers? Huh? Oh, here. Okay. There are two speakers here, but do they reach that point? Well, if you are not able to hear me, please let me know. Otherwise, you can move to the front. I see a few seats vacant. Okay, so we meet on Wednesday and your tutorial is on Thursday. Any other point? I think people are ready to go. So.